This is my third video in a series about how to reach exponential growth in certain graph with logarithm scale, and at the same time understand better about the meaning of logarithm and also how we can reach ratios in this kind of graph, which is very useful in many situations. And so I make use of this very interesting and very special graph about coronavirus cases growing with time. And here I recap a little bit how we can use it to estimate the growth factor in time. For example, this straight line here represents a growth by a factor of 4 in 5 days, because the horizontal axis is representing 5 days, and this length vertically represents a factor of 4. And you can see that this corresponding to a lot of cases in this graph, more or less lying in on a line in this direction, and also representing at the same time a 33% daily growth. Now I'm going to further explain and what we really see in the exponential graph at the same time when we are estimating the ratios and also expecting the constant ratios so we maintain in the graph. And I also use this applet to explain directly the comparison between these two graphs. Okay, one is the exponential curve, and the other one is obtained after transforming to a logarithm. That means the vertical axis now plotting only the logarithm of the original y values. And here in the third applet, okay, I particularly highlight this ratio of a factor of 2. That means, for example, from 600 to 1,200, it is a doubling. Okay, that means it is being multiplied by 2, and it happens in about 5 days. Okay, in this exponential graph. Now, if you drag along this axis in the exponential curve, you will find that actually, if this is a really exponential function, then this constant ratio of 2, okay, happens within the same amount of time. That means about 5 days in this case. So look carefully, no matter where you move along this line, and you will expect that in 5 days, you will expect the number to be doubled. Now, this is also the some very important characteristics of exponential growth and exponential function. And at the same time, if you transform it to a straight line through the logarithm, right? So on the right, you have the logarithm recorded. Now, this also is shown, right? But more clearly through the straight line. So that means with the same periods of time, the increase, the absolute increase in the vertical scale here is always the same. Now, why is it always the same? If you look at these two values, for example, 1,000 to 2,000, it corresponding to the logarithm, okay, 3 to 3.3, because logarithm 1,000 is 3, logarithm of 2,000 is 3.3. So it is always a constant of 0.3, which is just log 2. Okay. Similarly, if you check 800 to 1,600, it is also a difference of log 2. That means 0.3. Okay, that's why on this graph on the right, the vertical distance is always the same. But on the left here, the original graph, it is the ratio being maintained. Okay, which is not easy, of course. When you usually read a curve like this, you may not be able to notice so easily the ratio. But I think after examining these two graphs directly, and you may have a better understanding about their relation. Now, if I change the exponential graph, then you can see that this range is also changed. Okay, that means it is still marking ratios of 2, but it happens in a shorter time. That means the curve is steeper. So on the left, you can also see the time is shortened, and the slope of this line is greater. Okay, and or on the other hand, if I flatten it a little bit, okay, so that you will need more time to double, okay, in the exponential graph. So something like this, you need about more than 7 days to have the numbers being doubled. So on this on the right, then the line here is not so steep now. Okay, the slope is smaller. Okay, and that but they still maintain a particular slope. Okay, so you can have a check. Maybe you can compare with another graph. For example, I now put another graph for your comparison. If this is another exponential growth, okay, and from point P to point Q, represented by the red line, here in this red line, you will find that it takes longer time to double, and so the slope here is not so great. Okay, it is the slope is smaller than that of the green line. And similarly, if I make it steeper, let's say, or maybe now parallel, okay, or here it is steeper, so it takes shorter time to double in the red curve, and then you have a greater slope for this red line here. Okay, and how about I change to other factor, so you can, for example, consider 3 times. So it shows the length, right? How long it takes for each curve to raise to grow to 3 times the original value. Okay, and the constant distance here should be log 3 in both graphs. Okay, so I hope that this graph will help you to understand again why the logarithm is so useful, and after the transformation, in what way the slope represent the constant growth rate. Okay, and then also the time for the original value to grow by a certain factor. And at the same time, you may understand better the exponential curve, right? How in each exponential curve, actually, if you are looking at certain growth factor, and it is in fact a constant, right? Depending on this value, of course. So maybe I also show you this value here. For example, if I look at the case of originally, okay, this is about doubling in 5 days. Okay, that means if you take 5 days, then the value will grow to twice the value. And here, the factor you can see in this curve is about 1.25. Okay, so it has a growth factor of 1.25. That means each day it is increased by 25%. That's why each day you will expect to multiply the value by 1.25. And after 5 days, that means 1.25 to the power 5, you can use the calculator to check it. It should be more or less becomes 2. Okay, it is amounts to a factors of 2. If you take it to the power 5, that means this is what happens in 5 days. Okay, so maybe you can explore these relations in any other ways you like. Hope you enjoy and make good use of this graph for you to for your understanding of exponential functions and logarithms.